Hi everyone, today I would like to talk about very important concept namely linear MMSE, linear mean square mean estimator. So let me just remind you what I discussed in the last video. I will put a link in the description to the last video as well if you have not already watched that. In the last video we talked about orthogonality principle and we talked about the fact that x minus x hat is orthogonal to x hat. This is the estimator, and the whole quantity is residual. So residual is orthogonal to the optimal estimator. Right. So, and then after that we talk about the MMSE estimator of the random variable. Let's say y after observing that the x is equal to little x. So finding the MMSE estimator for random variable y after observing x is equal to little x. So we saw that the best estimator in that case, x hat, is equal to, let's show you this y hat now, is equal to expected value of y given x equal to x. So this is going to be the best estimator after observing some data, right? But then we talk about that this estimator in general is not going to be linear. So this is in general nonlinear and might have a very complex form, might have very complex form. So we said that this is the reason why we limit ourselves to the class of a linear estimator, linear MMSE estimator. Very important. What do I mean by linear MMSE? The linear MMSE estimator is a class of estimator in such a way that y hat equal to expected value of y equal to x is equal to a x plus b, right? Why ax plus b? Because remember the expected value of y given x equal to x, this is a function of x. This is g of x, this is a function of x. As I said, I'm going to release some videos about the comprehensive overview of video and article, comprehensive overview of the random variable and everything you need to know about random process and random variable. But just to remind you, note that expected value of y given x equal to x is equal to integral, let's say that they are continuous, integral of y f of y given x dy. So you are summing over all y. So what remains is only the x part. And that's why this is a function of x. So this is equal to ax plus b. Okay, great. Perfect. So now let's see how to find the optimal a and b. This is a very important problem in the literature, in the estimation literature. Finding the optimal a and b for a linear MMSE. No problem. We are going to follow the steps that I outlined in the MMSE Part 2 and also MMSE Part 1 and MMSE Part 3, right? So the outline is as follows. Step 1. Define the estimator. First, define the estimator. Y hat is going to be ax plus b. Great. So we have a form of estimator. You need to make sure that this step is defined correctly. Good. Step 2. Construct the MSE, mean square error, which is defined as expected value of residual square, which is defined as expected value of y minus y hat square. Good. Step 3, differentiate MSE with respect to A and B. Remember, we are trying to find the optimal parameter A and B and set them to 0. Set them to 0. Step 4, plug the optimal parameters in part 3 in the MSE expression to find the optimal MSE. Okay, so this is the step-by-step method on how to calculate the MMSE, and also optimal MMSE and also optimal MSE. Okay, very good. So let's apply to this problem. And let's see, we have a closed form solution and closed form, very nice closed form solution. Okay, good. Step 1, we already defined our estimator. Step 2, we are going to write it like this. This is our MSE. It's going to be expected value of y minus ax plus b all square. Let me make sure I all square. Put it here. Okay, good. What's the next step? Expand this. Expand it, right? Let's expand this. We get y square plus ax square x square plus b square plus 2abx minus 2ayx minus 2by. Okay, good. Let's simplify. Let's bring the expectation inside. We get expected value of y square plus a square expected value of x square. Remember, a and b are deterministic. Great. Plus b square. I don't need to write the expected value of b square because it's equal to b square. Plus 2ab expected value of x minus 2a expected value of yx minus 2b expected value of y. Good. Let's move on to the part step 3 here. So step 3, differentiate. Let's call this one j, like a convention for an objective function. Differentiate j with respect to a and b, and set it to 0. Let's do it here right now. So round of j, there are two parameters. Round of j, round of a is equal to 2a. I'm using this equation currently. Let's name it from now. 2a expected value of x squared plus, remember b is constant when you do it, differentiate respect to a. 2b expected value of x minus 2 expected value of xy. So this is expected value of yx is equal to expected value of xy, right? Equal to 0. The form of like a system of equation. J round of b. We get 2b as a third term plus 2a expected value of x minus 2 expected value of y equal to 0. Okay, so let's make it as a form of a system of equation in a matrix form. This is 2, this is 3, and let's write it like this, as follows. This is A and B, and this is gonna be the right hand side. I'm gonna make this one bigger. Good. So we can see that everything in the equation 2 and 3 are both divisible by 2. So first, before putting in a matrix notation, we will divide them each by 2. Great. So if you divide it by 2, what would happen is that you get this one. This is where the coefficient of A goes, expected x squared. Now, this one becomes ex, and here we have expected value of xy, and for the second row corresponding to equation 3, we get expected value of x and expected value of, and no expected value as a matter of fact. This is gonna be 1. And this time we're gonna have expected value of y. Good. Great. We call this one 4. We call this one our A. We call this one our Z. And let's call this one W. So AZ is equal to W. Therefore, Z is equal to A inverse W. Okay, so we have a good practice in finding the inverse of a matrix, 2 by 2 matrix. Let's apply that here right now. If A is this, what is the inverse of A? A inverse is equal to 1 over the determinant of A. Swapping the element of main diagonal, you get x squared, and then negating the element of the other elements diagonal. Okay, fantastic. Now, what is the determinant here? Remember, we had a note here. I will write it again. Note, if A is A, B, C, D, then the determinant of A is gonna be AD minus BC. Great. So what's gonna be the determinant of A? It's gonna have a very interesting form. Expected value of x squared minus expected value of x squared. Right? These two are different. 1 negative ex, negative ex, expected value of x squared. Good. Great. Let's observe this. Let's observe this equation for y here. Let's on this one. What is this term, guys? If you look at this one and ask yourself, what is this expression? The denominator, expected value of x squared minus expected value of x squared. All right, this is just a variance of x. Exactly. So note, variance of x, usually denoted by this sigma squared notation, is equal to expected value of x minus x squared, or expected value of x squared minus expected value of x squared. Great. Okay, perfect. Now let's just multiply them out together and let's see what we get. So you see that already we are getting some very close form solution here. So let's switch the color here. Let's see what is z equal to. Z is equal to now 1 over variance of x times 1 negative expected value of x, negative expected value of x, expected value of x squared, multiplied by the vector w. Vector w is e of xy and expected value of y. Good. Let's multiply them to see what we get here. Let's not first worry about the 1 over variance of x, but let's just first multiply these two quantities together. So what we get is 1 over variance of x times these two. So this is 2 by 2. This matrix is 2 by 2. This is 2 by 1. The result then is going to be 2 by 1. So this is going to be e of xy minus e of x, e of y. That's this one. I have some time to write it like this. E minus e of x, e of y. The other one, though, is equal to e of y, e of x squared minus e of x, e of xy. Good, great. So this is corresponding to z. Let's switch the color a little bit and remind ourselves what is z. Z is a, b. Therefore, a is equal to 1 over variance of x times divided, means that times e of xy minus e of x times e of y. Check, as a matter of fact, I can bring this one here, and let's look at this equation with each other for a while. What is the numerator? What is the numerator? If you look at this one and use the knowledge of your probability knowledge, you're absolutely right. The numerator is covariance of x and y. Covariance of x and y divided by variance of x. Look at this. A has a very, very nice form. A is equal to covariance of x and y divided by variance of x, right? Let's remind ourselves a little bit here what we mean. Note, covariance measures the amount of variation between x and y, right? So covariance of x and y is going to be expected value of x minus mu x times y minus mu y. So if you multiply these two and expand it, you will get something like this: xy minus ex times ey, which this ex is mu of x and this ey is mu of y. So for convenience, I just use ax and ey. Okay, perfect. So now we know what is a, what a is. What about b? So a has a very nice form. Good. But what about b? What is b? B is equal to 1 over variance of x, right? But what is the numerator? The numerator is e of y, e of x squared minus e of x, e of x, y. Minus of x. Okay, so that's not that bad. It's not a really bad expression actually, what we have here. But the question here is that if I leave b as it is, let's say I leave b as it is, can I go ahead and simplify b slightly more? I can leave it as it is, but in order, since if you look at a has a very nice form, but b is not really that interesting, especially the numerator. So let's see whether I can do something more. Let's look at the numerator of b. In the numerator, look at this term. I am going to, before writing that, I'm going to write a note here for you guys. Note, variance of x, as I said before in this video is expected value of x squared minus expected value of x squared. Therefore, expected value of x squared is equal to variance of x plus expected value of x squared. Good. Let's go ahead and apply this to this numerator. Let's see what we get. Therefore, what we get, b is equal to expected value of y times variance of x plus expected value of x squared minus expected value of x, expected value of x, y. Good. Divided by variance of x. Okay. Now, let's simplify this a little more. We get ey variance of x plus ey expected value of x squared minus ex expected value of xy divided by variance of x. Okay, now let's look at this equation with each other. This equation, it's very interesting. Something very basic to remind you all. Note, if you have a plus b over c, you can write this a over c plus b over c, right? Let's do that here. Let's see whether we can simplify this further. This one, the first term has a variance of x. The denominator we have a variance of x. Let's cancel them out. You get ey. Good. So now what you will end up here is ey e of x squared minus ex e of xy divided by variance of x. Look at this one. Look at this. I can factor from e of x. I can factor from e of x. What do I get? I get e of y plus factoring from e of x. I get e of y minus e of, I get e of y, e of x minus e of xy divided by variance of x. What is this term? Let's all look at this one. What is this term? You're absolutely right. This is negative covariance of xy. Because covariance of xy was expected value of xy minus expected value of x times expected value of y. So this is negative covariance of xy. Perfect. We're almost done. Almost done. So the result is going to be ey plus, or let's put a minus, let's absorb the negative sign here, e of x times covariance of xy divided by variance of x. We can leave it as it is. We are done. It's good. But let's take a look at some very interesting fact here. What is this? I'm gonna go up. Look at this one. Look at this. Look at this. Isn't that just a? This is exactly a. Right? This term is exactly a. Therefore, B optimal is expected value of y minus a expected value of x. Done. These are optimal coefficients that we just found in a very, very nice fashion and very closed form solution, very good closed form solution. Okay, so we have B and A. This is good. We are done with the part 3. But now, what if I want to find the optimal MSE, optimal expected value of residual square, mean residual square, which was a step 4, right? So in a step 4, we will plug A and B in MSE expression. No need to integrate, no need to derivative or differentiate. All we have to do is simplify to find a closed form or a very nice solution. Good. Let's find the expression that we had for the MSE. This is the expression that we had for MSE. I'm gonna copy this expression here, go down, down, down here. I'm gonna plug it. Okay, place it there, place it here. Good, 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 good. This is gonna be expected value of residual square. Good. I'm gonna plug the actual A and B here. Okay. So I'm gonna only plug B and leave A as it is, because inside B we have A as well. So if I only plug B, then I will have everything in terms of A. So let's just do that. E of y square plus A square E of x square plus, let's just plug this one, E of y square plus A square E of x square minus 2A E of x E of y plus 2A E of x. Now instead of B we plug EY once minus 2A E of x. That's what we had, because it's a negative A square x square. Good. Minus 2A E of xy minus 2 E of y. Now instead of B we're gonna plug once E of y square. The other time we're gonna have 2 E of y, because there is a negative negative, and 2 E of y 2A E of y, yes. So hopefully we have done it correctly on. The time for simplification now. Okay, we have 1 E of y square here. We have 1 EY square, but let's see if we have anything interesting somewhere else. Yes, these two cancel out with this one. We will get E of y square minus E of y square. So this term is going to be variance of y. But let's just continue. Now we have 1, we have this cell, 1, we have this cell, and 1, we have this cell. Similarly, we have this one minus A square E of x square. This two we're going to take it together. It's going to be great. Okay, this one, this one, this one, and this one. Right. Now these and these are going to cancel out. So we're going to have this one now. Let's take a look at this one. 2A E of xy minus 2A E of x E of y. So it would be better if I just starting from here, I do this one here. I factor from 2A and then do this. Okay, good. Let's do some simplification. This one become variance of y. This one become variance of x. So the resultant value is going to be y plus A square variance of x. Let's write this better. Plus 2A, what was this term? Negative covariance of x and y. Great. Okay, good. Let's now plug the equivalent value of the A. So here we will have variance of y plus covariance of x and y square. Remember what A was? A was covariance of x and y divided by variance of x divided by variance of variance square of x times variance of x minus 2 times covariance of x and y square. So there is one covariance of x and y in the numerator of a. Multiplied by this term become the covariance square of x and y divided by variance of x. All right, they're almost there. So this is gonna be variance of y plus. So this one and this one will cancel out. We will have one variance of x. Look at these two terms, this one and this one. If you subtract them, we will have only negative covariance of y, covariance square of x and y. So perhaps it's gonna be this minus covariance square of x and y divided by variance of x. Good. Now is the time to factor from variance of y to get 1 minus covariance square of x and y divided by variance of x, variance of y. We are done. Now, I want to remind you something. Note, write a note here. I want to remind you something. Remember, guys, the correlation coefficient that we had in a statistic? Pearson correlation coefficient. Pearson correlation coefficient. What was Pearson correlation coefficient? Measured the linear, very important, the linear correlation between two quantities. What was the definition of that? Rho was denoted by rho, not p. Rho was equal to covariance of x and y divided by a standard deviation of x and a standard deviation of y. So they're almost there. Our result is going to be variance of y minus rho square. That's it. Because variance of x, sorry, a standard deviation of x square is variance of x, a standard deviation of y square is variance of y. So if you square the denominator, you get variance of x times variance of y. Okay, so this was MSE. Okay, so this is the optimal MSE. Let's discuss about this equation a little bit. Let's have a line break here. Let's discuss. Let's have some intuition here. Okay, intuition. Let's write it there. Intuition. I am gonna go ahead and copy the equation of B here. I'm gonna write the equation of A because it's too simple to write. This is B. Use the same color. A is covariance of x and y divided by variance of x, and then MSE was what? Was variance of y divided by y minus rho square. Let's get some intuition about these equations. If this was what happened under what case? It happened under when y is equal to ax plus b. If x is 0, or if x is 0, x does not exist, if x is 0, this means that, let's have this one here. If x is 0, this means y is equal to b constant. Let's see what we get here. If x is 0, or the best thing to say is that what if a is 0, not x is 0. If a is 0, then y is equal to b, which is a constant. In this case, what would happen here is that b is equal to ey, right? B is equal to ey, and MSE is equal to, what's gonna be equal to? It's equal to variance of y over 1 minus, okay. Before talking about that, under what case a is 0? What should happen for a to be 0? A is covariance of x and y divided by variance of x. Well, when a is 0, this means that covariance of x and y is 0. This means that e of xy is equal to e of x, e of y. Well, what does it mean? It means that x and y are independent, or they are uncorrelated, let's say. Seems that x and y are uncorrelated. So remember, note, if x and y are independent, then they are uncorrelated. But if x and y are uncorrelated, then it doesn't mean that they are independent. So here, x and y here are, assume that if they are independent, the covariance is 0. Or you can assume that x and y are uncorrelated. Since we don't have any assumption, we can make it. You can say that assume x and y are independent. If x and y are independent, the covariance is 0. So if x and y are independent, perhaps it's easier to write independent, or it has some nice intuition, are independent, then a is 0. Well, guess what? If they are independent, we just said that they are uncorrelated. This means that the rho is 0. So you get 0 here. So the MSE becomes variance of y. Remember in the first part of this video, I said that we want to estimate a random variable, let's say y, based on some constant. We realize that the constant was mean of that random variable. So this equation says the same thing. The constant, which is b, is equal to mean of that random variable. And the MSE is equal to variance of that random variable. Okay, good. So that's the first case. It completely matches our intuition. Now, what if the rho is equal to 1? What would happen if the rho is equal to 1? Meaning that x and y are perfectly correlated. X and y are perfectly linearly correlated. Perhaps this is good to say that perfectly linear. This is Pearson coefficient, right? So x and y are perfectly linearly correlated. Then what does it mean here? This means that MSE is 0. The MSE is 0. The mean square error, if the rho is plus minus 1, perhaps it's better to say that. Plus minus 1 is either perfectly positively linear correlated or perfectly negatively correlated, right? This means that MSE is 0. The mean square error is 0, right? So if x and y are perfectly correlated, the mean square error is 0, of course, right? Because you can exactly recover x from y, or you can exactly recover the random variable y from the x. Exactly. No loss in the information. So this means that perfect recovery and no loss of information. Okay, so you see that these three quantities, I will use them also later on in the next chapter when I use this square. You will see that you can also use this equation for this square. Okay, perfect. So this actually concludes my lecture about the linear MMSE. So again, like always, if you like the video, please subscribe to the channel, like and share the video with your friends. I have written also an article available in the internet. I will have a link in the description that explains the linear. See all this equation available, so you don't have to write them down. And all the explanation, the intuition I just gave you, they're all in that article. Please check that article as well. So I will stop the video right now and I will see you all in the next video. Thank you so much.